Yeah.
to you.
Yeah, thank you. Thank you, Erica. So I'm Shane, and as Erica introduced, I'm the graduate student here. So today I want to just talk about the black hole, nothing like really theoretical things, but it's more of a general idea and then what's the depictions of black hole we think it would be like. So I start with this title, which is hey, black hole, show yourself. It's because we call these kind of objects of a black hole. But if you look into the sky, we do see stars. We see some of the beautiful things that's shining out there, galaxies. But can you find any black holes in this image? This is the image taken by the James Webb, so it's a pretty deep and a fascinating image in here. So when you think about black hole by its name, you might think it just say something that is probably a black dot, a black spheres in the skies, where might blocking everything's, where you can't see it. And today, for today's topics that I will just let you know, tells you about things about black holes, like are they actually invisible or are they actually like emitting some really strong light in the sky? And what makes us think that black holes are interesting? Where why do we want to study black holes? And what kind of weird or um, intriguing properties they have? And eventually, I want to let you know like how can we find black hole in the sky, just like it actually exists in the image like this. It just we don't know. Well, before that, you probably won't be able to know how to find them, but it still exists in this image. So to begin with, I want to give you an idea how we discover a black hole. So black hole is actually a theoretical object. It's not what we observe in the sky. We do not see a supernova in the sky and then, wow, that thing is really bright. Let's call it supernova or stars in the sky that we observe every day. Black hole is actually the first thing that discovered in the theory, and it's all begin with the Einstein's field equation. So basically, in 1915, Einstein came up with an equation that can describe the gravitational field in a more general way. That it generalized gravitational theories into something that is more can describe the space-time together that the Newtonian physics cannot. So based on these equations, the same year, there's a genius scientist called Schwarzschild. He solved that equation. Remember, it's a nonlinear equations, which is very, very difficult to solve. But this genius mathematician, he actually solved this equation within a year and then came up with a solution that telling us there is something weird in the space. Well, not in the space, but there's a theoretical object that is really weird, where you can write down a radius of that object, showing the equation here that telling you that even the fastest things in the universe that cannot escape if it get into that radius. And then we call that the Schwarzschild radius. And within the radius, it actually encloses one thing called the singularity. And it's a very, very weird solutions from the Einstein field equation where we can't really have an idea of what that singularity is because everything becomes infinity at that point. And later on, scientists just give it a name, call it a black hole. The reason that they call it black hole is because when you pass beyond the point of Schwarzschild's radius, nothing can actually escape from there. And just like the little animation up there showing you that it's actually a circle in the sky that will blocking all the lights coming toward across it. And just let me tell you how genius this Schwarzschild is. He came up with the very first exact solutions from the Einstein field equations. It took people 40 years, more than 40 years later, to come up with a second exact solutions. And it is done by the Roy Kerr. He came up with a solution that telling us that black hole can actually spin just like a star, just like our sun. And spinning black hole now is thought to be more common than a non-spin black hole in the universe, because after all, everything in our universe is actually spinning. And such angular momentum will be conserved, and it will be the same case for the black holes. So let's talk a little bit about some of the regions that nearby a black hole. So on the left-hand side here, it's a Sheng-Chieh black hole, which is a black hole that is not spinning. So you will see a singularity being enclosed by the event horizon, and event horizon is exactly described by the Sheng-Chieh radius as shown in the previous equations. And when the black holes start to spin, there will be more or weirder things could happen around the black holes. Now, when we talk about the Sheng-Chieh black hole, it has just one point singularity. But when the black holes start to spin, the singularity will actually expand it and become a ring. And the event horizon, which a surface where the light cannot escape, will also become more of a ellipsoid. And outside of that region, there is another very interesting thing called the ergosphere, which is the region where the space-time itself being twisted, and so nothing can stay stationary within that certain region, which is showing down here, called the frame dragging effect. So it's basically the whole space-time is moving according to the black hole spin, and you cannot just stay there and not moving. When people are like observing you when you're getting close to the black hole. And on the top right, it's showing the NASA simulations of two black holes rotating each other, and what would happen when the lights pass through the black hole, pass through such a strong gravitational field, how it's being twisted and bended when you see it in front of the black hole. So I think frame dragging will be probably one of the interesting effects given by a spinning black hole, but people are always asking about what if we get really close to the black hole, or what if we fall into a black hole, what would happen? And at that point, I think the frame dragging, which moving you unwillingly, will probably not the worst thing you should worry about. So when you get too close to a black hole, you probably won't falling into a black hole just like that little bear friend, just like falling in and then yelling no. It's actually something weird could happen. Because of the really strong gravitational field close to a black hole, the gravitational field differences between your head and your feet are so large that it will actually stretch you extremely hard, that you become, they call it spaghettified. And so we call this effect of spaghettification, where when your foot gets real close to the black holes, it's not simply just stretch you, just like you're like going to see a chiropractor or things like that. It actually will tear you apart into the atomic scales, and then you become a flow of plasma flowing into a black hole. So it's probably not a good thing to get close to a black hole like this. And not being said that there are lots of like materials surrounding the black holes, and then they probably will also tear you apart. So just not a good idea to get too close to a black hole. It's good to view from the far away point, but definitely not. You don't want to get too close to it. Well, but if you unfortunately really get too close to a black hole, and then now you want to say goodbye to your lovers, to your friends, to everything that whoever love you, the only thing is that when you get too close to a black hole, you might not get a chance to say goodbye to them. That's unfortunately. So that's another point, that you don't want to get too close to black holes. The reason that you won't get a chance to talk to them is because that we communicate through light. The information is passing through light speed. But when you get too close to a black hole, the time and the space being twisted so hard that it become really, the time flowing really, really slow when you get too close to a black hole. And at that point, when you're waving your hands to your friend, whoever on the other stations or anything like that, when you're saying goodbye, that goodbye will probably take infinite time to get to them. And if you wave to them, you better keep in that hand waving posture, because that will be the last thing they see you when you're falling into the black hole. It's simply because the time is just flowing so slow. When I'm waving hand, just like I'm standing in front of you, I'm saying, hey, goodbye. I'll be probably just like frozen like this in front of the black hole. And that will be the last image you see me staying there. It's going to take an infinity or take infinite time for you to see me falling into a black hole. So in conclusions, just don't get too close to a black holes. And if you get too close to the black holes, I'm sorry, there is no turning back point. And also there's no way for you to communicate with your friends or anything like that. That's how bizarre the gravitational field is when you get too close to a black hole. But as long as you stay far away from it, you will be fine. Now, since we talked about some of the properties when you get too close to a black holes, but black hole is actually quite simple things. We only need 3 things to actually describe a black hole. Or with these 3 things, you can come up with any kinds of black holes you want. And definitely, if you don't want to get to a black hole too close, you need to study like these 3 things, and knowing that how you can avoid to get too close to them, right? So the first thing would be the mass. So how heavy the black hole is, and then the spin is how fast a black hole can spin. And last thing is the charge. So you basically can charge up a black hole. But the charged black holes are not so common in our universe, is simply because it will be neutralized by the materials around the black holes. But for the mass and the spin, we can have all kinds of masses, all kinds of spins of black holes in our universe. So far, we have talked about the black hole theory. We have talked about, in theory, what would happen when you get too close to a black hole, and how we can describe a black hole. So since I said that the black holes are theoretical, astronomical, not even astronomical, but they are first discovered as theoretical objects. It's really take more than 50 years for people to actually found a black hole in the sky, in our universe. Before that, everything is just a guess. It's just a educational guess here. And when this object was first discovered or detected, people realized that there's actually black holes in our universe. And this very first black hole being detected is called the Cygnus X1. It's a X-ray binary. And on the left-hand side, you're seeing the X-ray image of such objects. And on the right-hand side, you see what is the theoretical prediction of what's going on in this X-ray binaries. So basically, since it's so bright in the X-ray band, it has to be something that is really powerful that can emit such enormous energy in X-ray. and the only thing we could think of is probably a black hole. And it's a black hole accompanied by another blue supergiant, which keep feeding that black holes. And when black hole eating things up, it also will throw things away. As you can see in the sort of like this theoretical depiction, here you see two bipolar jets coming out from the black hole. So this is the very first object we actually confirmed or indirectly confirmed that black hole are an actual existed objects in our universe. And these black holes are so-called the stellar black hole, and they are actually formed from stars. When a star running their fusions, they have enough support from that energy to support a star to maintain where they are. But when they ran out of fuel, so they have nothing to create the energy, they will start to collapse. And then eventually everything will keep collapsing as long as that star is heavy enough. And eventually it will collapse into a black hole. But before that, it will eject most of its materials outward and triggering so-called the supernova. So basically what we see in the sky right now for all those supernova, we could expect there are black holes at the center of the supernovae. And this is the sort of like the theoretical prediction of how a star actually turns into a black hole. And in 2019 or 2017, sorry, probably in 2019, people have come up with a very brilliant way to actually see a black hole. And it's actually not seen through any of the spectrum type. It's not seen through light. It's not seen through the photons. It's actually seen through a very, very unique way. So what they're doing is they build detectors that is large enough that they can actually detect a very, very tiny vibration in the space-time or any vibrations in the world. So what they do is they build this sort of like two long legs of this facility, and they have a real precise, very, very accurate, not X-ray, but laser that shooting through all these tubes. And those tubes are very so sensitive that they can even detect a little tiny vibration coming from the dropping of a mug from one of probably the scientists in that facility. And that's how sensitive this whole detector is, so that they use it to see the ripples in the space-time. So you can imagine that they shoot two laser beam out in two directions. If there is a wave coming in one direction, you would expect that laser being twisted a little bit, but this direction will remain the same. So they can look at the differences between these two lasers and then figure out what's the ripples of the space-time. And then from there, they can trace all the way back or do some theoretical simulations to figure out what things caused the space-time ripples. And from their reconstructions of the signal, they found that it's actually two binary black holes that's rotating with each other and then causing the ripples in the space-time. It's not the ripples of like gas or like water, but instead it's the space itself is actually being dragged back and forth. And such signal can actually propagate all the way through the entire universe and being captured here on Earth. So this is the very first the direct detection of the stellar black holes. Before that, we look at the hot gas surround the black holes, we look at the light emitted by the black holes and guess that there is a black hole. But right now we have a relatively robust detections that probably there are still a mass black hole out there that we cannot see using all kinds of telescopes, but these unique detectors. But black holes are not simply just still black holes. Black holes are not, as I said before, that black hole can be described by three simple parameters. So you can imagine that there are black holes that as heavy as our sun, or sorry, it should be heavier, but a little bit heavier than our sun. There should also black holes that is way much heavy than our suns. And in fact, these black holes are expected to exist in every galaxies, and we call them the supermassive black holes. They usually have the mass of 1,000,000, even 10 millions of a sun. And on the right-hand side, it might be not so clear, but this is a galaxy. This is the optical image of the galaxy. You can see it's a elliptical galaxy. It's kind of like a fuzzy shape here. But if you look closely, you will see a jet that coming out from the center of that galaxy. And this is the jet that can only be engined by a supermassive black hole. And this is how powerful they are. They can actually outshine the entire host galaxy from there. And on the left-hand side, this is a theoretical simulations that people think, or scientists think, what's fuel the supermassive black holes up, and then create such a powerful jets out or outflows that can be seen across the entire galaxy. So far, we have no idea how these black holes are made or how they are created. We think, if you think about the stellar mass black hole, they have a mass of maybe 10 solar mass, which is the mass of sun, or it could going up to hundreds solar mass. But these guys are way much heavier than that. And you cannot simply just collapse all the stellar mass together to make these gigantic monsters in the universe. So we are now still thinking about what is the origin of these supermassive black holes.
I just have one thing to add. That
yes.
Galaxy M87 there, that optical jet coming out of the central black hole of M87, that is easily imageable by amateur astronomers just with a little telescope in their backyard patio. That's not something that's so exotic that only the biggest telescopes in the world can see. You can image it yourself and prove it to yourself that it's there.
Well, that's great. That's good to learn that. That's really great. So that basically saying that how bright it is. Yeah, so I would imagine you also seeing this like blurring things, but also a little bit bright strip coming out from there.
Yes, the jet, not just the galaxy, the jet coming out of the galaxy.
That's very fascinating. Okay. Yeah, because I always view this image through the Hubble telescope and things like that. But it's good to know that. Yes. So yeah, that's simply telling us how powerful these sort of like we call them the central engine or the active nuclei, galactic nuclei. In order to give you some of the size comparison of how big a stellar mass or a stellar black hole and a supermassive black hole could be like, you can look at this image here, where this could be some stellar mass black hole, which has size of like 6 astronomy units, or maybe 560 million miles. And comparing to our solar system, where we have the Earth in the green orbit, and then the Jupiter and Saturn. So this is some of the normal stellar mass black hole you can see, or you'll find in universe. But compared to the supermassive black hole, it's just extremely small. Where you see if we zoom all the way out, this is our solar system. This is the Neptune, and then the orbit of Saturn is something around here. And compared to a black hole that's seated in the center of the galaxies, this is how big a supermassive black hole could be like. That's the size difference. And it's really sort of like think about the size difference between these things that could just like blow your mind out that how can we have these things in the universe and how are they actually being made? Everything is still not very clear for us right now, but we do try our best to figure out what's the origin of these black holes. And there are supermassive black holes. They can also be seen in different wavelengths. So on the left-hand side here, it's a Hubble image. So basically the optical image, something close to what you can use your phone to get. And then these are the supermassive black holes that's seen by the Hubble image. And on the right, it's the Chandra image. So basically the X-ray image of the supermassive black holes. So because of the very complicated structures around these black holes, it can emit different kinds of light throughout the wide span of wavelengths. And in fact, these things are actually quite far away from us. And that's the peak where we think most of the supermassive black holes are were active. And since we have the very first detection of the stellar black hole by LIGO laboratory, here we are showing you is another direct image or the very first image of the supermassive black hole ever been made by scientists. It's basically connecting all kinds of the radio telescopes across the entire Earth to make a really large telescopes in order to capture this image here. And this is the very first direct image that, the very first direct image of a black hole, of a supermassive black hole. For a stellar mass black hole, unfortunately, it's way too small for us to actually see them. But this is the black hole that you've seen in this galaxy. That's the same black hole ejecting the materials, creating these outflows. And we took the very first picture of that black hole as you've seen from here. It's basically just a glowing donut. It's not something really fancy, but we do really excited to see this because even though the supermassive black hole has been really large in size, compared to the size of galaxy, compared to the size of our universe, they are actually really, really tiny. And we really need some very unique or special techniques to actually see these black holes. And that's the very first image. We also have, if you search for this Event Horizon Telescope, they also have an image of the supermassive black hole in our own Milky Way. And you will find another donut there. So I've been talking about stellar mass black hole, and I talked about supermassive black hole. So where are the black holes that may have a mass between 1,000 to like 10,000? That is the great mystery still in astronomy that we are hardly finding any intermediate mass black hole so far. We can see the stellar mass black hole through the X-ray binaries or through LIGO. We can see the supermassive black holes in each of the galaxies, and they can eject enormous outflows or become like quasars. But where are these intermediate mass black holes? We don't know yet. Is it just they are just being hiding out there, or they are just not there, not exist in our universe? So there's actually a observations where people actually find some clue about this intermediate black holes. It's a black hole they estimated to have a mass of like 8,000, so much lighter than a supermassive black hole of 1 million mass, but also much heavier than a yes, and a of a stellar black hole. So if you look at, they look into this star cluster, and then they trace some of the stars in these star clusters. They trace their movement through a couple of years, maybe 10, 15 years, and then they find that these stars are actually orbiting nothing there. So they didn't see anything at the center of these stars, but they do orbiting at that point. So by estimating how these things are orbiting, they actually think that there is a intermediate black hole at the center of all the orbits of all the stars around it. So this is kind of an evidence of there might be an intermediate black hole exists in our universe. It's just that we are not, we just basically can't find them because they are not eating things up, they are not glowing, they are not doing anything, it's being quiet out there, a truly black hole out there. But through tracing the dynamics of stars around it, we do have a way to infer their positions there. So finally, I've been talked about the black holes, the what would happen if you get too close to a black holes, and what the actual black hole looks like. But now I want to end this up with I think this is one of my favorite movie called The Interstellar. In that movie, they hired the Nobel laureate Kip Thorne to do the simulation for them, and this is what they got. And this is actually the real physical simulations of a black hole, what they think the black hole would look like when there's materials orbiting around the black holes, and how black holes could heat up that materials. And they put in some of the cool effects to make it look cool, but the whole shape and how the materials moves around that black holes are actually physical motivated. It's a true simulation of a black hole. And I want to end up my talk with showing you this black hole. And if you're interested in that movie, I would definitely recommend watching it. It's a really nice movie. And I haven't talked about like the wormhole part, but there's a theoretical prediction of the connections between the black hole and wormhole, since they both twisted the space-time extremely hard. People are guessing that right at the center of a black hole, it could exist a wormhole, but who knows? Maybe in the future we have a probe or something that can actually go into the black holes. I don't know, but we'll see in the future. So this is my talk about the black holes. Thank you. Yeah.
Yeah. I have a question about spinning black holes, which you mentioned.
Mm-hmm.
Most of the black holes seem to have some kind of spin associated with them. Conservation of angular momentum. If a star that's spinning, like our sun, for example, now it would have to be much more massive, would collapse into a black hole, that spin or that angular momentum that it had would be conserved when it collapsed into the black hole. Also, if you had a binary black hole where you have an accretion disk coming around the side and spinning around it, as that collapsed into it, all that spinning accretion disk is angular momentum, and that would be conserved too. But if it collapses, if it all collapses down into something like, say, a neutron star, then you can figure out how fast it's going to spin because the neutron star has a radius associated with it. And it's just a straight angular momentum calculation. But a black hole has a singularity, which is infinitely small and infinitely dense. So how does the angular momentum get conserved to a point that's infinitely small and infinitely dense? Does it just have infinite angular momentum and infinite spin rate, or what exactly?
I don't think the angular momentum will be like just like, you know, like collapse into a one single point singularity. So in the curved black hole, if you spin the black hole up, the singularity actually will stretch out.
It's not a singularity then. It has dimension associated with it.
Through that Einstein's equations, the energy is part of the curvature space. So it's the whole solution, the pair solution that includes energy and angular momentum throughout the space time, not just the matter.
Well, that will be on me for you. I'm just thinking of angular momentum from physics, not necessarily relativity.
The angular momentum in the space itself.
Okay, I understand. That was a good question, though.
Yes.
So when you're like going into a black hole, would you see yourself spaghettify or like?
Yeah, that's a good question. So when you get into the black hole, well, besides getting spaghettified, when you get too close to a black hole, we see things through the reflection of the lights, right? So you will see the light reflect from the back of your head, and it will go so fast around the black hole, and then you will see yourself. You will see the back of your head when you get really close to the black holes. And so I guess, yeah, you will probably see yourself getting spaghettified.
But eventually even pulls the atoms apart themselves, right?
Yeah, right. So it's not, well, but I think it's also related to how heavy a black hole is, like the whole process. So it might just like done in a second, or it could take years for you to get spaghettified. But yeah, to your questions, I think you will see yourself getting spaghettified.
I get how you can measure mass. Let's say, Sag space star. You actually have orbital information, and using basic Newtonian physics, you can figure out a mass from those orbitals. Yet we talk about masses quite readily about distant galaxies where we cannot measure those orbitals. So what are the data sets that you go to measure mass? If you can only measure two things, you can measure spin or measure mass. How do you measure mass if you have no orbital data or accretion data?
Yes, that's a very good question. So the most straightforward way is to measure the dynamical mass. So basically you look at like just the star that you talked about, like we look at the stars surrounding it for 20 years and then we figure out what's the mass of it. But for distant galaxies or distant black holes, it's not a feasible way to do it, but instead you can look at their spectrum. So the black hole would not just simply emit light in like X-ray or optical, it also will emit in radio. So you have multiple features or patterns you can follow, you can derive to know how so right now we have the black hole like this. So it's like this, and then this, and this. But in fact, it's not simply just an accretion disk and then the whole feature that the light bending by the black holes. There's also surrounded by lots of gases. And these gases will be heated out by the black hole as well. And also the light coming out from the black hole will also reflect light from the gases. And combining all these informations, you can do optical observations or do the observations or even the radio observation, you can figure out roughly what's the mass of this black holes are. But these are only for the supermassive black holes. For the stellar mass black hole, you probably need the binary systems. As long as it's not binary, if it's something like the intermediate black hole like this one, you wouldn't notice it's out there.
Question about intermediate black holes. I know that those are and few between. In fact, I don't even know if any of them were detected until recently. I understand how a stellar mass black hole forms. You get stars up to masses of 100, solar
Right.
masses, whatever, and it collapses down, it loses some, blah, blah. You get black holes like 8 solar masses or 15 or 20 or 50 or something like that, right? And I understand the supermassive black holes, they all seem to be at the middle of galaxies. And the bigger the galaxy is, the bigger the central black hole is.
Yes.
I know there are millions or billions of solar masses. It's almost like a different type of black hole. It
Yes.
forms differently or something. But then you get in the middle at 1,000 to 10,000. How do those form? Those can't form from stellar collapses because the stars aren't massive enough. And it seems like they would be bigger if they formed in the middle of galaxies or something. So maybe they're just not there because they're not there. There's just not the population.
Right.
I don't know. I mean, what are your thoughts about that?
So they're actually like two direction, right? Either it's not existing, like this is we're just like looking at some maybe projections effects or something like this, or it actually exists, but the birth of these intermediate black holes are probably distinct from the stellar mass black hole. So one of the guess, or not me guessing, but like people doing the research on intermediate black holes are thinking about that these black holes are actually formed pretty early in the universe, and they also form at the center of the galaxies, some really small dwarf galaxies.
Oh.
But then these galaxies being destroyed either by bypassing another galaxies or like the interaction between different galaxies, that it's being stripped or it's been thrown away from its host galaxies.
Well, some globular clusters are stripped centers of galaxies too.
Right, so they get stripped out from the galaxies and then they sit there without any like people feeding them up. They are just like staying there forever because there are no materials or there are no gas, there are no things to feed them up. So they just exist there, sitting there and then doing nothing.
By the way, if you've never seen Omega Centauri through a big telescope, you need to.
Really?
Yes.
Can you image the horizon of these? Or too small?
I think it's too small. I think it's too small. I think the Event Horizon Telescope are not capable of like going down in the size of black holes. They are aiming for supermassive black holes unless I think there is another ambitious observations. What is it called? Lisa or something? They plan, but because the event horizon so far, its effective radius of detecting things are the half of the radius of the Earth. Now, if we put all these detectors, all these radio telescopes into space, in general, you can have as large as you can let it be as large as it can be. So people are talking about doing this kind of things like sending the radio telescope into space just to make a really large interferometry telescope. And by then we will probably be able to actually see the event horizon of some of the black holes. But I don't think it will be the case for this one. It's simply because it's probably not eating anything. There's no materials around it. So it's like the black, and then the background is black too. So you won't be able to see it. It's not glowing. I'm sorry. You got questions over there?
I was just asking about do black holes die?
Well, in theory, they do.
what would happen?
It will just like, and then just gone,
I think it
disappear.
actually makes that noise.
Probably,
Sure.
but well, but the sound does not propagate in space. But yeah, they do die. There's a effect called the Hawking radiation, and basically the black hole radiate away its mass, but it's a really, really slow process. So for any given black hole that is even a stellar mass black hole, it will take trillions of years for it to actually shrink and eventually evaporate it.
So when it dies, is it like it can't eat anything anymore, or is it like or is there like not enough like things to eat for it to like continue to live on?
Yeah, so it gets starved and it starts to die out.
So it's not just like it just like it can't eat anything when it just has to die out.
No, it can keep eating things. Right. So this is an interesting part of the black holes. It's actually just a singularity, and then things get infinity there. You can just keep throwing things into it. It will grow bigger, but it won't just like, there's no upper limit for the black hole.
Okay. So
Yeah.
when you know how like the black hole vomits, right?
Right.
Basically it eats everything and then like will it basically like kind of like rearrange like the atoms and stuff for it and like will it like create like new elements?
Well, I don't think they create new elements, because to create new elements, you need fusion. You really need to, hit the atoms together and then stick them together. Right, but because they get so fast and it's like extremely hot around black holes, everything being teared down to the plasma level, where basically everything is electrons or protons around the black holes. You can't really have you couldn't really have atoms around black holes, simply because it's way too hot around black holes.
And those bipolar
Jet,
conditions you
yes.
see there, they don't come from inside the black hole.
Yeah,
They come from outside the black hole, but near it.
yes.
So it's not the black hole spitting out stuff. It's the black hole creating those things, but those radiation coming out of both sides was never inside the black hole event horizon.
Yes, that's true. Yeah, well, in fact, the materials are not like really, people are thinking about like materials are actually not really touching the black holes. They might being heated up and then through certain mechanisms and then being redirected to the pole of the black holes and then become a realistic jet. Sorry, not the relativistic jet, and being ejected out from black holes.
Just like black holes have angular momentum and they have spin, they also have magnetic fields, I guess, right?
Yes.
And some very, very strong ones, I guess,
Yes.
right? Because those things get concentrated also, like
Mhm.
angular momentum does when
Yes.
something collapses down. So I think, is that right? Yeah.
Yep.
So that's what you see, those jets
Mhm.
coming out of both ends are concentrated magnetic fields.
Yeah.
Like the poles of a magnet.
And even more crazier, these magnetic fields will actually be shot out all the way to the galaxies and then affecting the evolution of the galaxy.
And they work, that matter, it works with magnetic fields because it's not neutral matter, it's
Yes.
charged plasma, so it's affected by magnetic fields.
Yes. They're basically boosting up the electrons and then shooting them out. So basically it's a electron shooting device.
And if they're aimed right at us, it's a quasar.
Yes.
By the way, an amateur can easily image quasars 10 billion light years away. It's not difficult. It's a telescope you can hold in your hand on your back patio.
Because they are like super bright.
Yes, they are. Even though a lot of them are even 10 billion light years away, you can image them. Yep.
Yep.
Okay, if there are no more questions, I think we'll wrap it up here. Thanks again for coming out, everyone. And yes, the weather is still a no-go, but if anyone wants to take a look at the telescope, stick around. And... Oh, do you have a question? No, I'm just trying to. Okay. Yeah.
Thanks. It's interesting. I'm trying to make it.
Versus anything? Yeah.